All right, hello everyone. I think we'll get started now. Welcome to today's session. Today is going to be organic chemistry. And as before, I've made this presentation with resources from Kaplan, AAMC, and New World, as well as a bit of like my own notes from when I took organic chemistry. So these are like the topics that AAMC says will be on the MCAT from organic chemistry. This is of course only 1 hour, so by no means exhaustive. I want to delve into each of these in a little bit, but I highly recommend that you review the content for all of them and make sure you have like a good foundation for organic chemistry. For the MCAT, it comes up in the first section, the chemical and physical foundations of biological systems, which is chronologically the first thing you're going to get on the MCAT. And in that section, they say organic chemistry is about 15% of the content, which means maybe like 9 questions you can expect, but it does change from test to test. Some people will say that their MCAT was very orgo heavy. Some people will say there's just like physics heavy. So it's not for sure that amount, but you can expect around that. And a periodic table is provided. This is like one of the few resources you actually get when you're taking the MCAT. So you don't have to memorize that, although this is, for orgo, it is mainly just carbon and hydrogen, but if you ever need, it's good to know that that's there. So for organic chemistry, obviously there's like a lot of different groups, like this photo kind of shows. Not all of them you're going to need. It's nice to have like a good foundation on nomenclature, which I'm not going to get too much into since it might take a while and everyone's kind of at a different place with that. But be familiar with like the names of things, because they might give you the name of something that you need to know the structure or vice versa. So it is multiple choice, so you have some ability to kind of guess, but it's good to be familiar, especially with like the extremely common ones, like that first line, like alcohols, aldehydes, things like that. These are the ones that, like from New World, they said were like the functional groups. So these are probably the ones you're going to see more often, and definitely the ones you should know. So for just carbon and hydrogen, alkane, ene, ine, and then the groups that have oxygens as well. So like ketones and aldehydes, as well as carboxylic acids. And we're going to get more into like the reactions with these, but it's good to be familiar. And then in terms of like nomenclature as well, the prefixes and suffixes, since it might not explicitly say like, oh, this is an aldehyde, but it might just give you the name and it ends in al. That's how you're going to know. In terms of naming, it's also important to remember the priorities. So this is just like a handy guide. So like, for example, the highest priority is carboxylic acid. So make sure when you're naming your different groups, you're aware of how the nomenclature works. So the first thing we're going to get into is the molecular structure and absorption spectra. So one thing in terms of organic chemistry on the MCAT in general is there's like a lot of lab situations, a lot of questions with experiments or how would you measure something. And so I put that kind of at the start of this. It's also mentioned in the start in the AAMC document. So these you might have covered in your organic chemistry class or at least in lab, but it's really good to brush up on. Visible region is like marked as Gen Chem. So I'm just going to do the other 3 here. So as you remember from maybe the physics review, there's like the light spectrum. The ones that for orgo are important is UV spectroscopy, but all you really need to know for UV is it's good for studying compounds that have double bonds or heteroatoms with like lone pairs. So a lone pair next to double bonds can also create a conjugated system. So just UV can help with conjugation. It's with like the pi orbitals. And so basically, if you remember like the HOMOs and LUMOs, the lower unoccupied molecular orbitals and the higher occupied ones, it can basically, in the LUMO, they can absorb the energy to go to the HOMO. So basically, a conjugated system could be shown through UV spectroscopy. You can also see kind of in the photo there, the ultraviolet light can be absorbed and excite the electron. So yeah, just like double bonds, conjugate systems. Infrared, we're going to go a little more into, but it's basically to help find functional groups. So this is what it would look like. You have like your sample and your infrared light, and what it actually does is like stretches and bends in the bonds. And that'll get you a spectrum that looks something like this at different frequencies. So different bonds stretch at different frequencies. We kind of talked about light and excitation, that equation at the bottom during physics. So I won't get too into that, but basically you'll look at like the intensity of the signals and at what wave number they happen. So they get stronger as you increase the absorbance. And from that, you can find out the different groups that are in your molecule. So this is like the entire frequency range. It would obviously be a lot to expect someone to memorize this. So I'd say the 3 important ones to know. An OH bond has a peak that's kind of broad. So it's like more like U-shaped than like a steep V, if that makes sense. And that would be around like 3,300 inverse centimeters. And so molecules with an OH would be like alcohols, waters, carboxylic acids. The carboxylic acid would actually be a little sharper, and that would be at about 3,000. You can also see here, it's a strong signal. Another one is nitrogen. So nitrogen, hydrogen, that bond, sharp around 3,300. And then C double bonded to O is also sharp, and that's around 1,750 inverse centimeters. So if you were given an IR, you can kind of find the functional groups based on that. Another important technique is NMR, nuclear magnetic resonance. And so again, this is what it looks like. It basically uses magnets, as the name suggests, to work with the fact that different nuclei have magnetic moments and they're oriented at random, but when they're in a magnetic field, they can either align with it or against the direction of the field that you're putting in. And so you'll get splitting patterns, and you'll basically have a plot of frequency versus absorption of energy. And the standardized method that they use on the MCAT is just an arbitrary value of chemical shift. So you'll see probably like a delta symbol, which we see, I guess the examples don't have it there, but that's just if you see the delta, it's just an arbitrary shift amount. And then back here, what you look for is the proton environments. So these graphs will show you like the different splitting patterns because protons get split. So for example, the first one here, there's the hydrogen that is blue. If you're looking at that one, it has no neighboring hydrogens. Like it's attached to a carbon, it has no hydrogens on the carbon next to it. So you use the n+1 rule. So 0 + 1, you're going to get 1 peak. And then as you can see, as it increases, you get more peaks. So if there's 1 neighboring hydrogen, you see 2 peaks. If there's 2 neighboring hydrogens, you see 3 peaks. If there's 3, you see 4. So that's how the splitting works. That's how many like peaks you see, and where those peaks are can be influenced by the shift and the different groups that you have in your molecule. So on the left is more for carbon, but on the right is the HNMR, which is more common. So for example, usually the rule is like if you're more polar, you'll be shifted, but you can see the different groups and where it would end up if you have a hydrogen next to one of those groups. Here's another maybe clearer version. This one's from UWorld. So shielded would mean it's not shifted much, it's upfield, and then downfield is de-shielded. And so common ones you can see is like the carboxylic acid is like the most downfield. Oh, and I guess also important to note that like the most shielded is just like your regular CH3, no oxygens or other molecules going on. So basically from HNMR, the information you can get is the chemical shift, so how far across it is, and that will show you what groups are around it. Integration is like how many protons or like hydrogens are in the environment, and splitting is how many protons are on adjacent atoms. So for the ethanol molecule there, if you're looking at the green hydrogens, so like the ones bonded to that carbon, they have 3 neighboring hydrogens, the 3 blue ones, and that's why there's 4 peaks. Then you'll see like the red one, since it's next to the O, there's no neighboring hydrogen, so it's just the one. And you can also see the shift will help you realize that the way that the most shielded ones are the blue because they're the furthest away from the oxygen. And then last is the blue. So the blue is next to two, the two green, and so there's 3 peaks there. So be familiar with reading NMRs. There's a lot of like practice available online, searching up and just trying to like guess what the molecule is or getting more information about the molecule. The next section we're going to look at is stereochemistry. So there's lots of different types of isomers. I think this flowchart from Kaplan is pretty good for explaining it. So isomers will have the same molecular formula, but a different structure. But there's many different ways that you could have isomers. So if they're not connected the same, that's a structural isomer. So like if one is just like a chain, whereas the other one splits up into a Y, but it's the same amount of carbons and hydrogens, that's like a structural, also known as a constitutional isomer. If they're connected the same way, then, but still a different structure, then those are stereoisomers. And if you could rearrange it without breaking any bonds, and you can get from one to the other, that's a conformational isomer. That's configurational if you actually need to break the bonds to change between. And that splits up into enantiomers and diastereomers. And basically enantiomers are non-superimposable mirror images, which we will get into. And then for diastereomers, there's cis and trans. So the first type is a structural isomer. So these all have the formula C6H14, but as you can see, they're just connected in different ways. Then there's conformational isomers, where it's like you don't have to break bonds to make one look like the other. So these diagrams, you can see there's like configurations called like staggered, eclipsed. You might have seen in your organic chemistry classes, but basically through these projections, it's the same butane molecule you're looking at, but it's just based on like how it's rotated. And you can see that the rotation, because of like the bonds between the different molecules or between the different atoms, will have different potential energy. So as you're rotating it, you can see the lowest energy is A and G, which are anti-staggered, because the CH3 groups are as far apart as you can get, whereas like the highest energy is where your CH3 groups are like in the same position. So when they're like both pointed up, for example, that's called totally eclipsed, like it's eclipsing over, and that's the highest energy. So the stability will depend on like the angles between the carbon-carbon bond. So you can see there's like 60, 120, 0. So eclipsed at totally eclipsed at 0 is the highest energy. And then in terms of figuring out for isomers whether things are enantiomers or diastereomers, if you have a chiral center, you can assign a priority. So a chiral center is like carbon that's bonded to basically 4 different things. And you assign priority. So like if X is your carbon, you assign priority by the Kahn and Gold prelog rules. And so that's basically, you want to put the lowest priority group in the back. So like the green D that they have. And you assign priority based on like the atomic numbers of things that are bonded. So if you have your periodic table handy, right? So like things like oxygen and nitrogen have a higher atomic number than carbon, so those will be higher priority. And if say you're bonded to like 2 different carbons, if it's still, you look at like the next thing over, and so maybe it's like on one side you have like a carbon bonded to a carbon, but on the other one it's carbon bonded to an oxygen, that'll be higher priority. So you kind of just like keep going down till you find a difference. And so you give them the priorities 1 to 4. You put 4 in the back, sort of, and then you see to go from like 1, 2, 3, do you have to go clockwise or counterclockwise? So as you can see on the left there, put the 4th priority in the back, you have to go clockwise to go ABC. So like 1, 2, 3 priority. So that would be R. And one way I think of it to remember it is like if you're looking at the top, it's going to the right, like clockwise is right at the top. And then the other option is S if you have to go counterclockwise. So all the chiral centers can be assigned a configuration, and from there you can determine whether you have enantiomers or diastereomers. So enantiomers, as we said, are non-superimposable mirror images. So that's like your hands. They're mirror images of each other, but you can't superimpose them. And so that would exist if all of the chiral centers are exact opposites. So say you have a molecule with two chiral centers, both of them are either R or S. If you have like an RR and an SS, those are enantiomers to each other because it's exact opposites. The other option is if you have like SR and RS, those are enantiomers. But the other relationships would be diastereomers. So like if you have one that's RR and the other is RS, it's not exact opposites, so those are diastereomers. So I think this visual kind of helps you figure out the relationship between those. If it's not like the exact opposite, it's diastereomer. Another further classification is E and Z isomers, and that's across a double bond. If you still assign the priorities, double bonds, you can't rotate the way you can rotate single bonds. And so there are two different configurations because it can't be rotated. You can either have the high priority things on the same side or opposite sides of each other. And so E is if they're on opposite sides, Z is if they're on the same side, and like the acronym that I learned in Orgo was Z same side. So if the Z is when they're on the same side. And so the next thing we move into is separations and purification. So this is like the section that I feel like is not covered in organic chemistry class, but probably in lab, but important to know because you will see a lot of things come up about experiments. So one is the extractions. So extractions, distillations, chromatography, electrophoresis, all of that stuff. So some of this you'll find in biochem. So like where it says BC, but the things that were more organic I put in here. So one example is like liquid-liquid extraction. You want to have, you've probably done this in Orgo lab, but add the solvent and then your stopcock, you'll shake and then the layers will settle and lower density will be on top. So then you can like open the stopcock, wait for like the higher density to leave and then close it. So that's like one way of separating liquids from each other. And then we get into distillation. There's three types that they mainly want you to know: simple, fractional, and vacuum. And the photo kind of shows the setup, so I won't get too into that, but it's good to know when you want to use each. So simple distillation is when the boiling points are at least 25 degrees Celsius apart. So it's pretty easy to separate, like they're not very close together. And you usually want them to boil below 150 degrees Celsius. So it's like the simple one, easiest to separate sort of. Also kind of the simplest setup. Fractional distillation is when the boiling points are very similar. And so you heat and then the higher boiling point compound recondenses in the fractionating column while the lower boiling point one travels through. So that column is kind of what's different between simple and fractional. And then like the collection is about the same. You collect the lower boiling point. Simple is the same there. And then vacuum distillation is when the liquid you're trying to distill has a boiling point over 150 degrees. So very high boiling things. You can see there's a vacuum source connected there. So it's good to know just like when to use each of those three. You might be asked like which distillation should you use. Chromatography is the next thing. So chromatography uses two phases to separate compounds based on either their physical or chemical properties. So the stationary phase, also known as the adsorbent, is usually a polar solid, and then the mobile phase runs through that, and it's usually a liquid or a gas. And so if it has a higher affinity for the stationary phase, it'll take longer to pass through. So like if you are hanging on, if you like it, it'll take longer to pass. But if it doesn't have a high affinity, if it's low affinity, it'll pass through faster. And so things separate at different paces. So examples of chromatography are thin layer and paper chromatography, which you might have done in Orgo lab. And so there's also reverse phase chromatography, as we see here, where your card is nonpolar and your solvent is polar. So it's already labeled here, I guess, but usually the stationary phase is what's polar as shown in like the normal phase. And then polar things have a high affinity, whereas non-polar things will move faster because they're not really like attached to the polar. It's similar to like the like dissolves like phenomenon. And then reverse phase, you're doing the same thing, but you flip it so your stationary phase is non-polar. And so it's important to just note that because they tell you it's like reverse phase or normal phase. You need to see like the thing that moves faster is that polar or non-polar. It's going to be the opposite of what your stationary phase is. So be aware of that difference, or else you might get like the opposite answer. Another thing is column chromatography, which can use polarity, size, or affinity to separate compounds. So this is like an example of a setup. You add the sample and pour a solvent over, and then the more similar it is, the faster it elutes. The more similar it is to the mobile phase, the faster it elutes. But if it's similar to the stationary phase, it'll elute slower. So this can be used. So for example, ion exchange chromatography, which I think kind of goes into biochem, but there's beads coated with charged substances. So things with an opposite charge will stay. So if you have like positive beads, your negative things will stick, but positive things repel, so it'll be faster for positive things to pass through. Size exclusion chromatography, you'll have like beads with little pores, and so smaller things will pass through, larger things will go through faster though, because they won't get stuck in the little holes. And then affinity chromatography is like you're specifically targeting different things, so you'll have like a receptor and antibody, so that's like a very specific format. Another thing they ask for is like separating enantiomers. So diastereomers have different properties, so they can be separated easier. Enantiomers often have the same physical and chemical properties. So one way is chiral column chromatography, which I think the diagram does a pretty good job of showing it, but basically you have like the mix of your R and S enantiomers, and you have a gel that's coated with chiral molecules, and they interact differently with a chiral solvent. So in the zoom in, you can kind of see the solvent is your mobile phase, but your stationary phase is chiral. And then things move slower down, like the S's are stuck up, whereas the R's move a lot faster. So you can see the actual example of the compound they were using, but one will elute faster than the other based on what you use for your phase. And so the next sections are like they have amino acids, lipids, and carbs, which all kind of cross over with biochem, but there are all organic compounds as well. So for amino acids, descriptions and such, you'll probably find like proteins are more biochem, but there are like some organic reactions we can talk about in terms of the synthesis. So as a refresher, as you probably know, that's what an amino acid looks like. And the alpha carbon is the one labeled there with the alpha. It's attached to nitrogen and another carbon. And so peptide bonds are when like two amino acids join, and you can see the bond labeled there. Another thing is that they exist as Zwitter ions at neutral pH, because the nitrogen will have a positive charge, but then the carboxylic acid has a negative charge. So at like your neutral 7 pH, it's a fun fact, or like an interesting aspect of them. But again, that stuff, the properties and the amino acids you should have memorized anyways, the basic ones, but that's like a biochem thing. For Orgo, you might want to know how to make them. So the two that they mentioned were Gabriel syntheses and Strecker syntheses. So I think the photos here basically show it, but a Gabriel synthesis will generate an amino acid based on like the substances we have there. So one's potassium, I think it's pronounced phthalimide, I think, and a diethyl bromomalonate. I'm not very good with pronouncing these. I guess I've only listed them on paper, but and an alkyl halide. So there's the alkyl halide. So first you have like the SN2 reaction, and then you use your alkyl halide, which is like the next step going down there. And you can basically end up, after adding heat, you end up with an amino acid. And you can kind of see, I think this photo does a good job in like keeping in red what turns out to become your amino acids, you can see where it's made from there. And then the other way is Strecker synthesis. This is a specific one where they made alanine, but a Strecker synthesis has an aldehyde and ammonium chloride, and then that makes an imine, which is that like nitrogen structure there, and then you have potassium cyanide, and so then you get an aminonitrile, and then last thing is heat. In both of them, you need heat to get rid of the H3O. And you end up with, in this case, alanine. So I think like for seeing these might help, but it's better to like, if you work out the arrows and the mechanisms yourself, these are like the two ways they say for like, it's good to know on how to make amino acids. Next thing is lipids, which again, very much biochem. One thing that I'll mention is steroids. So the concept of a steroid, it's like the backbone will be 3 cyclohexanes and a cyclopentane. So like hexagon, 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 pentagon. So like an example of cholesterol is desogestrel, but like that's just one of the examples. But it's good to know that like that's what makes something a steroid, because you might get, I've seen questions like that, like which one of these is a steroid. So it's important to look at the backbone. Carbohydrates, again, a lot of biochem. But one thing is sugars can go between their ring form and then their linear form. So it's important to know that the way the arrows go, basically, as you're seeing there, to form a ring. And when you make that ring, so what they have is like the Fisher projection, and then you can turn it into, the rings are usually shown as like the hexagons, the Haworth projection. Different sugars will have like, which way is like the OH versus the H, will tell you what sugar it is. That's again more biochem, but it's also good to know that there's 2 forms, alpha and beta, when they're in the anomeric form. And basically, I don't know if I have, okay, so I'll describe basically for anomers. So the anomeric carbon is like the new chiral center you make when you make it into a ring. So it's like it was the carbon that had the carbonyl when it was in a straight chain. Now it's chiral after you make the ring. And so alpha anomers will have the OH on the anomeric carbon trans to the free, like the CH2OH group. And then for beta, it'll be cis to that group. So you can see it in the diagram there. Also, just like familiar, like vocabs to be familiar with. So as we mentioned, diastereomers are like configurations where like the R and S's aren't exact opposite of each other. And that can be further classified into epimers and anomers. So epimers are a type of diastereomer that differ at exactly 1 chiral carbon. So for the example we used, there was only like 2 chiral centers when we did like RS. But like if you have like 6 chiral centers or something, and there's only 1 that they're different at, that's called an epimer. And then anomers are a subtype of epimer that differ at the anomeric carbon. So at that specific carbon that we said, the one that's formed in the ring closure. So it's mainly in the context of the MCAT, you just need to know them for the sugars. So beware of like the alpha and the beta forms. Next thing is aldehydes and ketones. This is a pretty extensive topic. Like they split up into 2 chapters in the Kaplan book, but some highlights, I guess I'll say. So one thing is just like the general addition reaction when you have a nucleophile. So you have like your general aldehyde, the nucleophile will attack, and then the electrons shift up. And then because that oxygen gets a negative charge from those electrons shifting up, you can grab a hydrogen. And so you add on the nucleophile, and your double bonded O becomes an OH. So you reduce to an alcohol. That's like the general form. Hemiacetals and hemiketals are important to note. So that's basically when you react with 1 equivalent of alcohol. So when you react 1 equivalent with an aldehyde, you make a hemiacetal, and then when you react with one equivalent of an alcohol to a ketone, you make a hemiketal. So the name kind of suggests what it came from. And then once you add one more equivalent, you can actually make like the acetal or ketal. So you can see the hemi is basically that like one is an OH, the other is an OR. And then when you add another equivalent, that OH will change to an OR. So the hemiacetals and hemiketals, these are used as protecting groups, but I do have a slide on that, so we can get into that later. This type of thing also happens with nitrogens, and you can make imines. So nitrogen derivatives react with carbonyls to make imines, and imines can also tautomerize to make enamines. And that's basically just like where the double bond with resonance can shift. But this is just like the basic idea of still like your nucleophile attacking, but the name's different because you're adding a nitrogen pretty much. So these are different protecting groups. So our hemiacetals, acetals, and ketals, all that make a comeback. There's also different types of alcohols and amines. I guess while the slide's up and while you look at them, basically protecting groups, alcohols can be used as protecting groups or like other functional groups. And what a protecting group does is basically when you're reducing something, it can keep that part unreduced. So I think there's a photo. Okay, there we go. So if you had like that original molecule and you reacted it with a reducing agent LiAlH4, it would just turn both of your ketones into alcohols. But if you wanted to protect one of them, so say you wanted to keep the top one, you just want to turn the bottom one into an alcohol, you can form a ketal, as you see here. So you would have to add that molecule and protect it, then use your LiAlH4, and you can just reverse it with water, and then you'll have your ketone intact, one of them. So you can protect groups as need be. So as it shows here, like a bunch of different groups can do protecting. In terms of reducing agents, some are stronger than others. So for example, LiAlH4 is stronger than NABH4. And you can see the different types of reductions they can do. So aldehydes and ketones reduced into alcohols is pretty common. You'll need something stronger if you're trying to reduce a carboxylic acid or an ester into an alcohol. And then H2 and pressure also at the bottom there can get rid of double bonds. The next section is alcohols. And so for all of the sections, they say like nomenclature, physical properties. That's like, we've covered nomenclature at the start. It's also just good to know like the prefixes, suffixes, and the names of them. And then in terms of the important reactions, there's SN1 and SN2 reactions. What's important to know is that for SN2, it's concerted, so it happens together in one step, whereas SN1 is like two different steps. So you have like your leaving group and your bond go to the leaving group, and then the nucleophile attaches. So SN1 it's like in two steps, whereas in SN2 there's a backside attack, and then your leaving group leaves at the same time as the nucleophile is attacking, and that will reverse your stereochem, which is important to know. So just in general, like electrophiles, nucleophiles, an electrophile is attracted to electrons, so it has a partial positive charge, whereas a nucleophile has a partial negative charge because it's attracted to like nuclei, positive things. In terms of SN2 reactions, you have to kind of decide the electrophile. So in terms of like which area in here between like the red, green, and blue, it's fastest when it's like less sterically hindered. So in that case, that would be the primary, the red alkyl chloride. You can see there's like no other groups really around it. Whereas the secondary group has like the chlorine, and the tertiary group has like the methyl and the bromine. So it's best when there's like no other things around, because you have so many things going on at the same time. Steric hindrance can really get in the way. We also say things of like leaving groups, which is, if we go back to this, the Lg is the leaving group. So, I mean, the name pretty much explains it. It's the part that goes. Some things are better at leaving than others. And so, like, the best leaving groups are alkyl halides. And even within there, there's like iodine is the best, and then bromine, chlorine after that. Those are like the easiest, like if you have like a bromine or something, that's the fastest, like the easiest way to do an SN2, those will leave. Methylates, tosylates, those leave as well. Water is like decent, and then after that we'd say like not good leaving groups. So fluoride isn't as good of a leaving group. Carboxylic acids and stuff like that, those will not leave as easily. Also talking about like methylates and tosylates, these are pretty important structures as leaving groups in general. It's also like actually mentioned in the AAMC document of just like know the structures and how to make them. So put them in here for that. And then, okay, then we move on to carboxylic acids and their reactions. So one thing is, so the three they have is anhydride formation, reduction, and decarboxylation. So this is making an anhydride via condensation. So as you can see, by removing a water molecule, you make the anhydride structure. So like the double bonded O, then like an O bonded to 2 carbons, and double bonded O. Next is the reduction to a primary alcohol. So as we mentioned before, like LILB4 is like one of the stronger agents, so that would be a better one to use in this case. So that's lithium aluminum hydride, but NABH4 is not as strong, so that can reduce other things. It can reduce like ketones and aldehydes to alcohols, but it's not going to work to reduce a carboxylic acid. And so this is kind of the steps for reduction. First, you have like the double bonded O, and then form into an aldehyde, and then reduce once more to get to the alcohol. And then the next thing is decarboxylation. And so that's where you lose a CO2. And this can happen within a molecule, so intramolecular. And as you can see, the attacks going on. As I mentioned before, tautomerization is like going between the enol and keto form. Keto is more stable, so where you're double bonded to the O, but you could also have like the O single bonded next to a double bond between carbons. And that's also, this tautomerization can also happen not just for oxygen, but also with like nitrogen or something, so like imines and enamines. And for this specific reaction, for decarboxylation, you're losing a CO2. Then they have like the acid derivatives. So from a carboxylic acid, you can get to a lot of different other derivatives. So this is where I kind of have my notes from Orgo. So these are the different derivatives, and they're the most reactive and polar is acid chloride. So the R group can obviously be anything. So then you have your double bonded O and chlorine. Although I think any like halide will have the same property there. Then you have anhydride, as we talked about before. So the double bonded O's and then an O in between. Aldehydes and ketones, as we talked about, aldehydes are actually a little more reactive than ketones, partly because they're just less sterically hindered. You have the hydrogen instead of another group. Ketones and esters are about similar reactivity. So instead of like a greater than, it's a little messy, but it's like the approximately equal. And then, so an ester is R, and then the carbon's double bonded to an O, and then single bonded to another O with another R group. Then you have amides, so double bonded O and then an NH2 group. Then you have nitriles, which we did talk about before. So that's like the C triple bonded to an N. And then lastly, carboxylate. So that's, the resonance is keeping that one together because you have like the negative O and then the double bond as well. So it can resonate, making it more stable. So if we go back, this web is kind of showing the different ways to get between. So I took organic chemistry with Professor Falzone, so like these were the ones we needed to know. But in general, I think it's good to have like an idea of how to move between these groups and just like the effective priorities. One thing is, I don't know if this is like the proper notation, but in the top corner there, an ester, there's like the arrow going back to it. So there's a reaction called transesterification, where if you have heat, which is the triangle, and like a proton environment, H plus, you can change like the R groups on an ester. So that's like transesterification, you're just changing the groups. So if you have something else like an R with the double prime as an alcohol, you can change out the group on your ester. That was one reaction to note. You can move between amide and amine at the bottom there, which is a Hofmann reaction. So NaOH, Br2H2O. You can move from an amide to a nitrile. As we saw with anhydrides, those can be formed with H3O plus and heat. Or if you're starting with your carboxylic acid, you would need a base, and then an acid chloride can get you to an anhydride. And then just water can get you back to your carboxylic acid. So in general, like lots of different ways to convert between all the things here. Also, like from acid chloride to anhydride, it's basically the same reaction as basically an acid chloride and the carboxylic acid together with the base will make an anhydride. So you can see the same type of reaction going towards there. From a carboxylic acid to make an ester, you would need an alcohol, heat, and protons. And let's see, what else is worth noting here? In terms of making carboxylic acids, Jones is like, the Jones reaction is probably one of the more common ways. I think we also talked about synthesizing carboxylic acids anyways. And then if you add a base to carboxylic acid, you can end up with your carboxylate. So NaOH there. So these are like the main web of reactions. I have it formatted another way as well here. So for moving, if you're looking at just like to and from carboxylic acid, these are the different ways. The ones that are like labeled 1 and 2, you would need to do like in ordered steps. Otherwise, you can just put the reagents together. So again, all of the groups in order of reactivity to get from carboxylic acid to that group would be like the first row, and then to go from that group back to carboxylic acid. As you can see, it's mainly just like H2O or H3O plus they'll get you back. In some cases for like the ester, for saponification, you would need NaOH, H3O plus. And then as we already, again, we saw a little bit, but the different ways to move between the different groups is also labeled here. So like the absolute bottom one, LAH, would get you from like a nitrile to an amine. So like the first set of arrows is how to go from acid chloride to any of the other things. The next one is like from anhydride to any of the other things. So from like anhydride to ester, you would just need an alcohol. And to get to an amide, you would just need to add the NH3, which you can kind of see in the structure there, how that would attack, and you'd get the nitrogen attached there. So in general, for organic chemistry, it's just good to have an idea of how to move between the groups. If we go back to the way they described it, the relative reactivity of the derivatives, steric effects. So as we kind of talked about with like the SN2 reactions, you want to see like how many groups are attached, or like which, when you're actually drawing the arrows, what's more likely to happen, which attacks are actually like free to happen versus where is it like a lot of different heavy groups going on and harder to attack. So we talked about transesterification, hydrolysis. Okay. And then I think the last thing, so in terms of the groups, most of them are acidic, the functional groups. So you have your halides. So again, that's just like any halogen. So your X would be like bromine, fluorine, iodine, chlorine attached to a hydrogen. Hydronium ion obviously how we measure the pH scale. A protonated oxygen, positive charge. Carboxylic acids are also acidic. Amines that are protonated, sulfonic acid and phosphates as well are acidic. And then the main basic functional group is amines, but again, not when they're protonated, but just like the general amine. And this is more based on like the Bronsted-Lowry theory of acids and bases, which you've probably seen in Gen Chem, where amines are proton acceptors rather than proton donors. And then I think this is the last thing, phenols, oxidation reduction. So biological redox. So redox in general would be Gen Chem. A lot of this also overlaps into biochem because these are molecules you'll see in the electron transport chain. But basically, when you treat a phenol with an oxidizing agent, you get a compound called a quinone. So phenols are like benzene alcohols. So as you can see, you have benzene diol, P being para because they're across from each other. So again, just like the nomenclature is good to be familiar with. And if you react that with the oxidizing agents there, you get a quinone. So this one is the 1,4-benzoquinone. And so this is, you're basically taking a hydroquinone is what you'd call the original thing, and you're making it into a quinone. So the H's are going away and you're double bonding to the O's. Some of these are biologically important. Main one is ubiquinone at the top there, which you may also know as coenzyme Q in the electron transport chain. When it picks up electrons, it becomes ubiquinol, the one below. So it can, this structure is important to its function because in the electron transport chain, it's grabbing these electrons, and that's how it's changing between forms. So that structure as a quinone allows it to accept the electrons, become OH groups instead of ketones, and transport the electrons across. So in general, also, I would just maybe it's more biochem, but the structures that in class you might have only needed to know the names, like coenzyme Q or FADH, NADH, those things. I would say it's important to be familiar with what they look like. I think one of the questions on my MCAT was what is FADH2? Which one of the structures is it? So just because that does kind of overlap into orgo, I would say the things where you might just know the name of, even if you don't completely memorize, it would be nice to at least be familiar with the structure so you're able to recognize it. So NADH, FADH2, coenzyme Q, these things for class purposes, you probably never had to actually see what it looks like. You just use the name. But since the MCAT is so holistic, because in biochem you didn't go as deep into orgo, or in orgo you didn't go as deep into biochem. Since the MCAT is so holistic, it's good to know these things, especially I think they love testing where the two things intersect, where organic chemistry comes into biology. And that's why you saw for a lot of the topics, they were OC, BC, they were both. So the organic chemistry concepts that are involved in biochem are probably the ones they're going to ask about the most. With that, I think that's all for the slides. Yep. We have about 8 minutes left. If there's any questions, anything I didn't go over, anything you want me to go over again, feel free to unmute or put in the chat. If no questions, also feel free to just put how you're feeling about organic chemistry or how your prep is going in general. Are you guys more on content review, or I know everyone has different test dates, so any stage of prep is fine, but are you doing more practice questions, practice tests? How are things going? Questions? Nice. Yeah, I definitely found during my prep that content review, sort of what we did today. Nice. Okay, yeah. Well, it's important to have that base so when you get to the questions, you're not like completely like every term is unheard of. But I definitely think practice questions were the more important part of my prep, and definitely where I like saw my score improve the most. So I would stress the importance of practice questions, but I'm glad you guys are already doing those. I think people emphasize content review a lot, but you can do a lot of review through practice questions as well. What I found helpful as well was looking at like the answer explanations when I got things wrong, but even when you get them right, sometimes you guessed, or sometimes like you had half the knowledge to get you there. There was another way to also do it. So I think WAMC, World, whatever resources tend to have like good answer explanations associated with the question. So I would emphasize that. Yeah, otherwise, if there's any questions about other topics as well, it doesn't have to be Orgo. If there's any questions lingering from math from yesterday, physics, or the other topics as well, feel free to ask. Otherwise, what we have upcoming is there's a group study tomorrow, and on Saturday, there's also the Saturday sessions, which you guys probably know by now, but have been moved to Zoom. So they're no longer in person. So would love to see you all at those. Again, I'll stay back for any questions, but otherwise, thank you all for coming.
Jessica, did you have a question? Okay, cool. All right. Well, thank y'all. I'll go ahead and end the call then.
Thank you.
Good night, y'all.
Good night. No problem. Thank you for coming.